Hey there, future clinicians. Welcome to this explainer. I am so glad you're joining me today. We're going to take what might initially look like dry whiteboard physics, current, voltage, power, and translate it directly into something absolutely crucial: everyday clinical safety protocols. Grab your notes, because this is literally the foundation of every single electrotherapy treatment you're ever going to perform. But before we look at a single equation, I've got a really serious question for you. What is the quickest way to accidentally burn a patient? As your clinical instructor, my absolute top priority is patient safety. Look, electrotherapy is an amazingly powerful tool in our healing arsenal, but we have to start by understanding exactly how it can cause severe harm. If we don't respect the physics driving our machines, we're putting the folks on our treatment tables at serious risk. So here's our roadmap for this explainer. We'll cover 1. The clinical safety stakes. 2. Joules' law explained. 3. Real-world patient scenarios. 4. Core physics foundations. And finally, 5. Your quick revision guide. All right, section 1, the clinical safety stakes. Let's look at how the basic rules of electricity basically dictate if a treatment is going to heal or harm. This is where theory meets practice. We intentionally use electricity for therapeutic heat production. Think about modalities like shortwave diathermy or SWD and infrared. We actively want to generate heat deep within those tissues to promote blood flow and healing. But here's the catch, and it's a big one. Without incredibly strict safety checks and precise control over the equipment, this therapeutic heat easily crosses the threshold into causing severe burns. That line between therapy and injury, it's entirely governed by physics. Moving on to section 2, Joules' law explained. Okay, if you memorize only one thing from our time together today, make it Joules' law of heating. It states that the heat produced, represented by the H, is proportional to the current squared, multiplied by the resistance, multiplied by the time. This isn't just some abstract textbook formula. It's the literal recipe for how your machine generates heat inside human tissue. And notice that I squared part? That means current has an exponential impact on heat. It ramps up incredibly fast. Let's break down those crucial variables. Cranking up the current, the I, massively increases heat because, again, it's squared. Increasing the resistance, R, which we'll see in a second is often tied to skin condition, directly increases the heat too. And simply leaving the machine on for a longer amount of time, T, will also proportionally increase the total heat hitting the tissue. As the clinician, you are in control of these variables. If you lose track of the current, the resistance, or the clock, that heat is going to spiral out of safe therapeutic ranges before you know it. Section 3, real-world patient scenarios. Let's step away from the equations for a second and look at how this physics formula actually plays out on the treatment table with a living, breathing patient. This brilliantly illustrates the difference in everyday practice. Take scenario A. You apply pads to a patient with dry skin, which gives you poor contact. Based on our physics foundations, dry skin and poor contact spike the electrical resistance, the R. Plug that high R back into Joules' law, and boom, significantly more heat is produced right at the skin's surface, leading to a massive risk of burns. Now, versus scenario B. You ensure a moist medium and good contact. Water conducts electricity beautifully, which artificially lowers the resistance at the skin barrier. A lower R means less surface heat, giving you a safe, deep heat distribution. So, to prevent patient burns during your treatments, you absolutely must take these exact steps to deliberately keep that electrical resistance as low as possible. Step 1, ensure a moist medium. Use your wet sponges or conductive gels. Step 2, physically verify good, even pad contact so you don't have any high-resistance air gaps. And step 3, vigilantly monitor your time and current dials. You are the ultimate safeguard between the physics of that machine and your patient safety. Let's move into section 4, core physics foundations. Now that we know exactly why heat is generated and how to control it clinically, let's quickly review the underlying forces driving the machine itself. We'll start with voltage, the V. Simply put, voltage is the energy per unit charge. You can think of it as the electrical pressure, or the push that forces the current through the circuit in the first place. Bottom line, without voltage, there's no current, and without current, well, there's no therapy. Next up is power, represented by P. Power is the actual rate of that electrical energy conversion. Basically, how fast is the machine doing the work? It's calculated with a super simple formula. Power equals voltage multiplied by current. So P equals V times I. And the standard unit for power is the watt. So whenever you see a machine rated for a certain wattage, it's just telling you its rate of energy conversion. Now, when you take that power and you factor in the duration of the therapy session, you get the energy calculation. Energy, or E, equals voltage times current times time. E equals V times I times T. This isn't just trivia to memorize for a test. This is the specific formula we use to estimate the total heat or the total current dose that a patient receives over the course of their entire appointment. It's the cumulative effect of your treatment.
And finally, Section 5, your quick revision guide.
We've covered a ton of vital ground today, connecting physics with clinical safety, so let's pull it all together into one place. This summary table right here is your master cheat sheet for exams and your clinical practice. I highly recommend taking a screenshot of this right now. It perfectly maps out how voltage, current, resistance, power, and heat all interlock. You can see how Ohm's law, V equals I times R, flows right into our power equations, and ultimately down to Joules' law of heating at the very bottom. Keep this handy. It's the ultimate quick reference guide to everything we've just discussed. You can memorize all the formulas in the world. You can know exactly how to calculate watts, joules, and amperes perfectly on a written test. But as your clinical instructor, I want to leave you with this final, crucial thought. When you are actually standing next to that machine, will you remember to check the pad contact and skin moisture before you hit start? Physics dictates the heat, but your diligence dictates the safety. Think about that before your next practical session. Thanks so much for joining me on this explainer, and I'll see you in the clinic.